All right. So last time we were exploring the wonderful world of symmetries in quantum field theory, and we started out by saying, this plays the role of symmetries in nature and quantum field theory. I mean, you can't understate it enough because it's basically your guiding principle of how you write down a theory. And if we observe, conserved quantities in nature, it tells us there's a symmetry, and if there's, if we propose that there's some new symmetry, there must be some new conserved quantity, right? So it works both ways. And if you read, if you look in the literature, you see it used both ways. Okay. So we were going to talk about not only continuous symmetries, but some discrete symmetries, and then I'll touch on non-abelian symmetries today. Towards the end of these lectures, okay? But we started out by talking about continuous symmetries. We played some games, using basically the principle of least action, and along with the variance of the Lagrangian. We did some algebra and some hocus pocus, and we ended up finding that we could derive a condition for Nether's theorem. So the equation 12, or equation 11, right? So Nether's theorem tells us that if the Lagrangian is invariant under some transformation, you have a conserved quantity, right? And that would be the case when we apply the equations of motion. This thing goes away, right? And so we're left with the left side equals the variance of the Lagrangian. And if the Lagrangian is invariant under some transformation, then we have a conserved quantity. And that's the basis for Nether's theorem. Okay, so that was the most important part of that little derivation, right? And then we started to talk about, we wanted to see some symmetries in action, right? And we've only discussed or really worked with scalar fields, so there's not a lot of choices, but we found a couple, all right? So we started out by talking about this theory of a complex scalar field. So you have phi and phi dagger, right? And you have to treat each of those degrees of freedom as separate entities, right? But you can also formulate this not only in phi dagger, but you can write phi in terms of its real and imaginary parts, and then you can you plug that in into that Lagrangian, and you get something that is a little more familiar, right? It's a theory of two real scalar fields that we denote by phi 1, phi 2. Either description is, Lagrangian is fine, it's equivalent, but a lot of times it's a lot easier to work with this guy. So we ask ourselves, are there any symmetries? Can we spot any symmetries in these Lagrangians, right? And the first one we noted was that in the phi dagger case, we noticed that the Lagrangian is invariant under a unitary transformation like in equation 17. So we're just multiplying by some exponential, right? Some sine or cosines. And we notice that when we take phi dagger, we get plus e to the plus I alpha. And so anytime you have phi and phi dagger together, those transformation matrices, I guess you would call them, cancel out. Okay, so the Lagrangian is invariant. Okay, so that was easy. That was easy to spot. In the case of where we're working with the real and imaginary components of the original scalar field, the symmetry is a little more hidden, but it's actually just a rotation, right? It's a rotation in a two-dimensional plane, right? So you rotate phi 1 and phi 2 into some admixtures of phi 1, phi 2. And you can plug the new fields into the original Lagrangian, and you find that it's invariant. Okay, so it's invariant under this U1 type or SO2 type transformation.
Is it the same symmetry in terms of phi 1? If you write it as phi 1 and phi 2, that symmetry changes to this one?
Yes. Yeah. So it says something deep about I have the line here. Some from group theory, that U1 transformation can be mapped into SO2 trans. Whatever. I don't care about that part, but I just care about the fact that there's a symmetry there, and if I go and use my equations of motion or use my write down the Lagrangian, the action, work out the equations of motion, I can find what the conserved quantity is, right?
I know that SO3 is equivalent to SU2.
I don't know.
SO3 to SU2, but maybe I know that this is also the case.
Yeah, you got it. I don't know. Sorry. I know just enough group theory to get by in the day.
This happens when we discuss quarks.
Mm-hmm.
And then, we see that their SU2 is, since the quarks, the flavor and SU2 symmetry.
Mm-hmm. Yeah, the SU2.
It's for
The SU2 symmetry though has to do with the doubles.
Yeah, a mixture of U and D quarks.
Yeah, that's what the SU2 is. I thought the SO3 was
It's in
the different families. Yeah,
It's
different
different,
dimensions. Yeah. So those are two different symmetries. Yeah. But they are there, and they were put in by hand because we realized that there were some conserved quantities coming out of whatever experiments they were doing. What do we do? Okay, so I wrote down the currents, and then we went through kind of a convoluted way of verifying what we had talked about, the importance or the connection of all this stuff to Nether's theorem. And we derived in equation 28 something that's called the Ward identity or the Ward-Takahashi identity. And this we won't deal with a lot now, but it'll come into play, like I said, when we talk about vector fields, because it has implications on anytime you have external vector fields. You have to check that you're obeying the Ward identity. Okay. All right, so that did it for continuous symmetries, right? We wanted to talk about discrete symmetries because we obviously have some of those in nature. So we talked about how we formalize transformations. So we talked about Lorentz transformations, and then how to go from that to unitary matrix that that carries out these type of translations. And then we said, okay, well, let's look at some discrete symmetries. And the two that we know about from quantum are parity and time reversal, right? And parity is just space inversion, and time reversal is obviously reversal of time, right? And so we wanted to look into the implications of these symmetries. Right. So we know that for the case of Lorentz symmetries, we have this identity where we sandwich a scalar field between these two transformation matrices, and it's equivalent to the original field and just doing the transformation on the space-time coordinates of the field. Okay. So we kind of propose that maybe in analogy, their parity and time reversal have some analogous type of equations, right? So we introduced a notation we call P and T are parity and time reversal unitary operators, and so we propose that these guys obey the same type of relation. That when we sandwich the scalar field between parity and the inverse parity operator, or time reversal and the inverse time reversal operator, we get back something. We get back the scalar field with its coordinates transformed. Right? So either spatially inverted or time reversed. Okay, but the thing we know about, say, parity is that if we operate again, we should get back to where we are. Right? If we operate once, we inverted space, and then if we invert space back, we should get back to where we are. Right? So that meant that if we do two operations, we should get back to the scalar field. And that's all fine and good. I mean, we all accept that from classical mechanics and in quantum mechanics as well. But it has a kind of an important implication because it means that the field doesn't have to just come with a plus sign, right? Originally, we could define a field that when you operate on it with parity, you get a minus sign back out, right? And these are what we call odd fields, okay? And so, we say we observe parity, conservation of parity in nature. So that means that when we write down our Lagrangian, we want to make sure that it's invariant under this transformation, right? And so the obvious choice is if you're writing down a theory for scalar fields, you could just choose all the fields to be even, right, under parity, and then you're guaranteed that your Lagrangian is going to be invariant. But
is there a definition that when we operate the parity on both sides of phi, it's equal to phi when we apply parity on x? Is that a definition?
that's what it was kind of we postulated it. Yeah. That's what, it was a kind of an educated guess, right? That we know that that's the case in like Lorentz transformations. And we were guessing that, the same thing would hold for discrete symmetries, yeah. So you could always choose, you could be boring and always choose the fields to be even under parity. But say you go and do measurements and you find, one of my fields acting like it's odd under parity, right? So then we'd have to go back and write down a new Lagrangian, but we would still have to make sure that that the symmetry remains undisturbed, right? So if we wrote down terms on our Lagrangian, means we're going to have to, if we just have 5 fields, it means that this odd field, right, is going to have to come in pairs, right? So you would have some even field and some odd field, and to ensure that the Lagrangian remains invariant, they have to come in pairs, basically. Okay. Right, that's all. Everything I said. Yeah. Okay, that's all. Yeah, that's everything I just said. Okay. All right. So I think that's where I stopped. Right. And so what we can do is, I kind of alluded to this at the end last time, was that you can, when you write down a theory, you can impose any symmetries on it that you want. Right. You want to be, hopefully, you're guided by experimental or some sound idea. But you can impose any symmetry on your theory that you want. And a tool that's used a lot in the model building community is imposing discrete symmetries on your theory, especially for the cases of theories of dark matter, things like that. Right? So you define some operator Z, right? So this is it's a discrete unitary operator, right? And when it operates on the field, it gives you the field back, and in general, it can have some number, right? Because these type of transformations are. So here I have the technical, blurb about it. But Z is what we call a Z2 operator, and I think I just copied this out of some book, but it's the additive group modulo 2, which is equivalent to the multiplicative group of plus or minus 1. All that means that eta up there, eta sub A, has to be either plus or minus 1 if we're imposing the Z2 symmetry. Okay? So then at that point, it works a lot like parity or time reversal. Hey, we got one more. So you know that when Z squared is equal to 1, so when you operate twice, you would get back 1, right, or the identity operator. And so that tells you that the inverse of Z has to be equal to Z. Okay, so let's look at this in our cases for this complex scalar field. Okay, so just to remind you, we can write it in terms of phi and phi dagger, or we can write it in terms of phi 1 and phi 2. Okay, where those guys are the real and imaginary components of phi. right? And we've already seen that, these guys are invariant under some symmetry. So the phi dagger theory is invariant under that U1 transformation, and the phi 1 phi 2 theory is invariant under an SO2 transformation. But these theories are also invariant under another transformation, and the transformation that leaves this guy invariant is what? It's an exchange symmetry, so I can exchange phi and phi dagger, right? And I don't get back, and I get the original Lagrangian back, right? So in the case of the phi dagger case, the Lagrangian's invariant under this exchange or this interchange, right? And in the case of the phi 1 phi 2, it's invariant. You take phi 1 to phi 1 and phi 2 to minus phi 2, and you get back the original Lagrangian. Okay. And so this is a special type of discrete symmetry. It's what we come to know as charge conjugation, right? Because we have two fields that, if you look back at the Lagrangian, have the same mass parameter, so they have the same mass, right? But they differ under this discrete symmetry. One's even and one's odd, right? And so we call this charge symmetry, and it operates and works just like all of the discrete symmetries that we just talked about: parity, time reversal, and then the general Z2, right? And we always want to impose, that our Lagrangian, say we've done, hundreds of experiments, and we always see that charge is conserved, whatever this charge is. So we want to impose that symmetry on our Lagrangian, and so we always have to make sure that phi 2 comes in pairs, right? Because it's going to, under this charge conjugation, it's going to flip sign, and so you need two of those guys to cancel each other out, right? But like I said, it's our first glimpse into particles and antiparticles, because these are particles that are different under this charge symmetry, but they have the same mass. Okay, so we could identify one as the particle and one as the antiparticle.
You don't necessarily mean the electromagnetic.
No. It's totally generic. Yeah, we will. I think at the end of the semester, I'll couple this theory to a photon, and we'll make it'll be scalar electrodynamics. So, yeah, but right now it's just a general charge. So it could be, the electric charge could be, the strong force with the charge of the strong force, or the electroweak, or whatever. Yeah.
So whatever that fits in that definition is called charge.
Yeah. Well, yeah. 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 Yeah, because we haven't imposed anything. It's invariant under U1 transformation, which is what electromagnetism is, right? So in that case, we're safe in calling it charge conjugation, because it is like we're imposing the symmetry of electromagnetism. Yeah. Okay. But generally, you do call it charge. It's a charge under this symmetry. Yeah. Okay. So wanted to briefly just talk about non-abelian symmetries. We won't deal with those a lot in this semester. We'll deal with them next semester, but when we start to discuss the strong interaction and the electroweak interaction, because both of those are non-abelian, right? So basically 2/3 of the Standard Model is made up of non-abelian field theories. So it's very important, okay? But like I said, we'll go into that more in detail when we talk about vector fields and then fermion fields, okay? So let's start again with our toy theory of this complex scalar field. Okay, so I'm going to write it in terms of phi 1 and phi 2. And actually, I want to generalize this to n fields, right? So n, where n is some large number, okay? And the repeated indices here, i's, means I'm summing over all those. So there's, n copies of this Lagrangian, okay? And this Lagrangian you can show is invariant under the interchange of any of the indices. So if I interchange I with j, or 1 with 2, or 1 with 142, the Lagrangian stays the same, right? So there's some symmetry there, right? And the symmetry, it turns out, is just nothing but like a rotation symmetry, right? So you can think of these phi's as making up a vector, right? The components of a vector. And so this type of transformation where we're interchanging labels is basically like a rotation in this space, okay? So it's an n-dimensional space. And so we're doing an SON transformation, which is just a rotation. Okay, so we can write this in a more classical way, introducing our rotation matrices, right? And we know those guys are orthogonal matrices and they have positive determinant. Okay? And so I just have this blurb here about group theory. So like I was saying earlier, I know enough group theory to get through the day, and that's about it. I don't know, I'm not a group theory specialist. But it is, it's important in quantum field theory. It's particularly important, in model building, right? If you want to write down new theories and things like that. That's not something I do, so I don't play around with symmetries or things like that a lot. So I'm not an expert, okay? But I do the best I can, all right? Whatever I don't know, I usually look up.
I'd probably have to look back up my notes.
Yeah. I like I said, I've worked through SU3, which is QCD. I did that years ago, and I've worked through the SU2 cross U1, which is the standard model electroweak gauge group. So I know how to do those two, right? And I know what the different things I'm going to introduce here. I know what they are in those theories, but outside of that, I'm not a group theory guy. Okay. Huh? Yeah, the guts. Yeah. I shared an office when I was in grad school. I shared an office with a guy that was working on SU5, and another one was working on SO10.
Oh,
where there's like 32 Higgses or something.
I guess they are equivalent to SU5 is equivalent to
Probably. Yeah. I don't know. But I just know that they had bazillion particles coming out. They were super symmetry guys. All right. But anyway, so let me just talk about this real quick. All right. So we're going to impose this rotational symmetry on our theory. All right. And we know that an infinitesimal rotation is continuously connected to the identity matrix. Right. So the rotation, we can write an infinitesimal rotation as identity plus some small part, okay, some small part that's doing the rotation. And from the orthogonality of these guys, I can infer something about, what am I trying to do? I can infer that this matrix theta ij is real and anti-symmetric, right? Because I know if I do a rotation, then I do basically the opposite rotation, I'll get back to where I am, right? So it's got to be equivalent to delta ij. And so you can see that in the second line here, I'm flipping the sign of theta when I flip the theta, or the I and the j, because I know I need to cancel out those cross terms. All right, so it tells me that the theta is real and it has to be anti-symmetric. All right, and typically what we do when we go to, when we talk about things other than, this familiar rotation symmetry, is we'll separate out, we'll write down, the transformation in the same way, but we like to separate out this operator, this matrix, in terms of some parameter times a new matrix. Okay? And this new matrix is typically what we call the generators of the group. Okay. All right. So theta is an infinitesimal real parameter, so we're still dealing with infinitesimal translations. And you can think of these new matrices as being a base set, that spans the space that we're dealing with. Okay. And so A is an index, and it runs from 1 up to n over 2 times n minus 1. Okay, so it's just the number of linearly independent Hermitian antisymmetric n by n matrices. Okay, so it's just the number of matrices, the minimal number of matrices that you need to span your space. Okay. So you have some freedom when you go to write down these matrices, and typically what the convention is to write down a single non-zero entry of minus I above the diagonal and some corresponding non-zero entry of plus I below the diagonal. Okay. And then the diagonals, because you want this thing to be made up of, continuously connected to the identity matrix, the diagonals are just made up of plus or minus 1. Okay? And the prime example of this are the poly matrices, right? The SU2, right? that we're all familiar with. Okay, and so actually you can generalize a lot of this stuff from what you know about the poly matrices. For example, you know that the matrices obey a normalization condition that looks like this. So if I take two different matrices and I multiply them together and I take the trace, I get back twice the identity, okay, identity matrix. Okay. What else? What is going from here? Okay, so in equation 57, it's a proportional, and in 59, I'd set it equal, but what we're doing is we're pulling out that factor of I that we saw, that we were introduced above and below the diagonal. Okay, and like I said, these matrices, these T matrices, are called the generator matrices of our rotational symmetry. Right? Remember, we're talking about an SO rotation type of symmetry, and we have N fields. Okay. So n being the number of base vectors that you have. Okay. Right. How do I know that that implies that? Okay, so you use that argument that we used back when we talked about rotations in quantum mechanics, right? That you do two transformations and you stay in the space, right? It doesn't take you outside of the space. So there must be some equivalent one transformation that's equal to those two, right? So you say, okay, so two transformations is proportional to some singular transformation. Right? And so you can write down an equation that tells you that if I do this, two different ways, if I rotate, with A first and then B, or A first or B first and then A, I'm going to get something that's proportional to a single transformation matrix, right? And so what you can do is you can write down a complete analogy to the SU2 case. Where the F would be, the Levi-Civita tensor, right, and the T's are the poly matrices. You can write down a general commutator relationship between these generators. Okay, it's just that when you get to more complicated theories, these structure coefficients, the FABCs, can get more, obviously get more complicated. Okay, and we'll see. Like I said, we'll see a concrete example of that next semester when we talk about SU3 or the strong force. Okay, so equation 60 is what you might hear called the Lie algebra of the group, and there's a really good book. I don't know if it's in the library here or not, but if you're interested in Lie algebra or group theory in particle physics, there's a good book by Howard. I just went blank. It's called Lie algebras and particle physics, I think. And this is what I use to learn what little bit of group theory I know. Howard, I think of it, he's at Harvard, so it's in particle physics. Can't believe I can't remember his name. Like one of the most famous energy theorists ever. Anyways, I'll come up with it. So this specifies the Lie algebra, okay? In the case where these transformations commute, in other words, the right-hand side 0, we call these guys abelian symmetries. I don't know the source or where these names come from, but those are called abelian symmetries. And if the generators obey some Lie algebra like we have in equation 60, in other words, the right-hand side is not 0, it's proportional to some other transformation within the group, we call this group non-abelian. Okay, so anytime you see a theory that has a Lie algebra that looks like that, you know that you're dealing with a non-abelian symmetry. Okay. So we can play some games and try to figure out what these mysterious structure coefficients are, the guys that appear in the Lie algebra. Right. So we can use,
Howard Georgi.
Yeah. Thank you. Yeah. So yeah. So Howard Georgi, like Georgi or Georgie, is the author of that book and the father of grand unified theories and a bunch of other stuff. Okay. Anyways, so we can use, if we want to try to figure out what these guys are, we can try to use the things that we know about these generator matrices. And one that we know is, well, we know this in general, is that we can use the cyclic property of the trace. Right? So I can take, what am I doing here? So I'm taking our Lie algebra and I'm hitting it from the right with another operator, TD, and then I take the trace. Okay, and so then I use the identity that this guy, the right-hand side, is a delta function in CD times 2, right? And so I can write down what FABD is, and you can see that you can write it in terms of the generator matrices. Okay. And you can also learn something else by using the cyclic property of the trace. If you go up here and you plug in, or if you flip, switch some of the indices, and then use the cyclic property of the trace, and the fact that these guys, don't necessarily commute, you can show that they are anti-symmetric in the exchange of the indices, right? So up above, I started with FABD, and then I flipped D and A, right? And what I get is I get back minus ABD, right? So I started with FABD, right? No, I started with FBBA, right? So FDBA is equivalent to minus FABD, right? So that tells us that these guys are, we know what they are in terms of the generator matrices, but that also tells us that they're anti-symmetric under the interchange of the first and third indices. And you can go and show that they're anti-symmetric under any of these interchanges, except those that are cyclic, right? So those where I cycle through. Okay, so this is sounding just like the Levitt-Chavita tensor, right? Okay, and actually, there it is right there. Okay, so the algebra for the SO3 group. Okay. All right. What I'm going to do next. Try to remind myself what I want to do, where I'm going. Yeah. Okay, so we want to apply this stuff to a theory. Okay, and so let's again consider our complex scalar field theory. Okay, and we're going to generalize it to n fields. Okay, so again, I'm summing over these i's. So there's n copies of this Lagrangian. Okay. And so this is kind of a quick, so before we took the case where what did we do before? We had, we were just dealing with yeah, we were just dealing with real fields, right? So we took the case where we had real fields, and this gives us it's an abelian theory, right? So this what we're going to do is look at this charged, or this case where we have phi dagger, and see what's going on with this guy. Okay, so we're summing over the i's. Okay, we notice that the Lagrangian's invariant under these exchanges, right? Or we can say that it's invariant under a UN transformation, right? Because it's we have Hermitian conjugation going on here, so it's a different group. Okay. So again, we have some like a rotation type of matrix that operates on, our phi and changes it into another phi. Okay, but it's just again another rotation. And we can write this. You can play some games. You can write this in a more suggestive way by pulling out some factor of e to the minus I theta, where theta is your rotation parameter, right? And we use the fact that this determinant of this guy is +1. And I lost my train of thought. But the U tilde is basically what we call a special unitary matrix, meaning that the product of two special unitary matrices is another special unitary matrix. And we have n by n matrices, and they form this group SUN. Okay, so it's again just a group of transformations. There's n basis vectors for this space. Right? The only difference is we have this charge conjugation that we have to worry about, so it becomes a special transformation or a special group. Okay. All right, so let's see how this works. So we can write down our transformation matrix, the special unitary transformation matrix. It has to be continuously connected to the identity matrix. And then again, we'll write it in terms of some parameter and then these generating matrices. Okay. So again, we would find the fact that this guy has to be unitary implies that these operators are Hermitian. Right, and it implies that, let's see, equation 68. Wow, I signed something for that. Yeah. So 68, the fact that, so if you take that where am I? That U tilde and plug it into 68, you can show that these guys have to be traceless. Okay. And the index A, again, runs from 1 to n squared minus 1. Okay. And that's basically determined by the number of independent Hermitian and traceless n by n matrices. Okay. And so finally, you can just, like I said, you can just apply, the identity that you know and love, which is the trace of two of these guys gives you back the delta function, and you can specify the Lie algebra of your group. And the prime example that we keep coming back to for these cases is the case of SU2. So the case of the spin 1/2, right? The Pauli matrices. Okay, and in that case, we would find that our structure constants are nothing but the Levi-Civita tensor. Okay. All right. So like I said, don't worry about that stuff right now. I just wanted to introduce it to you and get the vocabulary out there. And we'll see it applied a lot next semester. Okay? All right.
Just in the case of SU2, it's Levi-Civita.
Yeah, but it's more complicated in the case of SU3 groups. Yeah. Okay. Okay, so we've talked about, we worked through the case of our phi cubed field, or phi cubed theory, right? We worked out the corrections to the propagator, the corrections to the vertex, and then we even looked at a 4-point vertex, right? Found that was finite. But we went through the whole process of renormalization, right? The whole, the way that it works, right? The way we canceled off the divergences with our counter terms. And so what I wanted to do in these lectures or these notes is to kind of take a higher level look at renormalizability. Okay, so we can generalize some of the things that we learned by. Wow, that's a lot of words. All right.
Yeah.
So like I said, we worked there with 5-cube theory in 6 dimensions. Right, we talked about how to cancel UV divergences with counter terms. And it turns out that this renormalization works at every order. So if you go up another order in your perturbation series, right, or go down, let's see, like we worked at G cubed, it'd be like G to the 5th or whatever. Okay, so, but you can apply the same recipe, the same algorithm to cancel off divergences as you go along. Okay. The hard part is computing the loops as you go up in those perturbation series. Okay. So it turns out that you can do this, right? And if the number of terms that you have to add as you go up in your perturbation series, if it's finite, then we can say that the theory is renormalizable, right? So no matter what order we compute at or where we cut off the perturbation or perturbative series, we can always write down counter terms that will cancel off any divergences that we run into, right? However, there are cases where that doesn't happen, right? And it turns out that every order that you go up in perturbation series, you have to keep introducing new counter terms, right, to cancel off these divergences. And so it would go on forever, and so you would have to end up introducing, infinite number of counter terms. And that's where we say the theory is non-renormalizable, okay? And, differentiating between these two, I mean, obviously this is desirable, right, to have a renormalizable theory so you can make hardcore predictions. But just because a theory is non-renormalizable doesn't mean that it's just complete garbage, okay? So non-renormalizable theories make up a lot of what we call effective theories, right? And we can use effective theories like we've talked about before to describe, the physics below some cutoff scale. Okay, so you see it all the time in the literature. People don't try to write down, some beautiful full theory of everything. They just try to write down a theory that can explain physics up to some scale. Okay, and those theories are, in general, they're non-renormalizable. Okay, but it doesn't matter because you're just, you're not integrating over the full range. You're just considering, the range below some cutoff. Okay, so if you hear the theory is non-renormalizable, doesn't mean it's garbage. I just wanted to get that across. Okay, so what I want to do in this first part is kind of formalize the conditions of renormalizability. All right, so we're going to basically derive a way that we can kind of superficially it's not an exact science, but it'll give us an idea of when we look at a theory, we can tell if it's renormalizable or not. Okay. So let's start by considering just the most general Lagrangian that we can build out of scalar fields, real scalar fields. All right, so this is the guy that we saw, I don't know if it was last time or the time before, but it's just the normal kinetic terms, the normal propagator terms for the scalar field, its mass term, and then we're summing over all vertices. Okay, so we're summing over starting at n equals 3, so our phi cubed theory, phi to the 4th, phi to the 5th, so on and so forth. So this theory contains all possible vertices starting at n equals 3. Okay, some of those are going to be renormalizable, some of them are not. Okay, so that's what we want to try to find. Okay. And the way we're going to do that is we're going to try to come up with a way to not derive, but to kind of gauge the degree of divergence of a particular diagram. Okay, so we've done this before where we looked at we wrote down a loop diagram, say, and we had that, the loop integral, and we counted how many factors of momentum there were, and we could say, oh, this guy's going to be divergent, right? Because we had more factors in the numerator than we did in the denominator. So we're going to do that, but we're going to do it in a more formal or general way, okay? So I'm going to introduce some notation just to make it compact. So E is the number of external lines in a diagram. So those are the guys that, either the initial or the final state particles. I, which unfortunately in this font looks like 1, is the number of internal lines in the diagram. Okay. L is the loop. Okay, so loops, obviously these are separate, so don't count. When you see a loop, we don't count those I's as internal lines.
By internal lines, you mean propagated?
Yeah, exactly. Yeah. And then we'll call this V sub n the number of vertices with n external legs in a diagram. So you'll see terms that look like V3, right? So that'll be our normal phi cubed type of interaction, or V4, which is 5/4, okay? So what we want to try to do is ask ourselves, do the momentum integrals from some particular diagram diverge, okay? If they do, can we renormalize them? Right? So that's what we're after. Okay, so like I said, we've done this before where we talk about diagrams that have closed loops, right? And we know that when we have that, we're going to have some numerator factor just from the measure of the integral, and it's going to carry in d dimensions. It's going to carry d factors of our loop momentum, right? And then likewise, the internal propagators or the denominators that might appear in this loop, they're going to carry inverse square powers of the momentum, okay? All right, and so what we've done in the past is basically, like I said, we compare, number of factors of loop momentum in the numerator compared to the number of loop momentum factors in the denominator, and just basically guess, So we saw if we had equal or more loop factors of loop momentum in the numerator, we guessed that it was going to be divergent, and we were always right. We always came out with poles, and we used dim reg, right? So what we want to do is generalize this. Okay, so I'm going to define something that's called the superficial degree of divergence. Okay, that's what this big D is. Okay, so what we were doing is basically this: counting the number of loops. So the number of loops times this D, right? So D fact. So if we had one loop, we'd have D factors of our loop momentum, and this would be the denominator part, right? So internal lines give us 2 powers of the loop momentum, right? And so for us, what we were doing was basically this, and anytime we saw D greater than or equal to 0, we said it's divergent, okay? All right. All right, so what I want to try to do is derive a more useful formula for D in terms of the parameters of our Lagrangian, okay? Because what we'll be able to do is, that helped us on particular diagrams, right? So we could use this when we had a particular diagram that we were going to compute, right? But just looking at the Lagrangian, we couldn't tell anything, right? If it was renormalizable or not. So that's what I'm going to try to do now, is try to come up with a formula for this superficial degree of divergence that is in terms of the parameters of the theory, right? So we can be able to look at the theory, look at the Lagrangian, and say, okay, this guy's renormalizable, right? So let's consider a nightmare scenario where we have this loop diagram that has E external legs, okay? There's going to be a bunch of stuff going on in that big black blob. But in addition to this, because we're summing over all possible vertices, we're going to have the tree level vertex, right? So I have a bunch of loops, but I'll have one tree vertex, right, that has E external legs, right? Because we're summing over all those. And we know that the value of this guy, we go back and look at our Lagrangian, the Feynman rule that we would write down would just be a factor of minus I ZE times GE, right? Where E is, again, the number of external legs. Right, so you compare the mass dimension of your tree level diagram, right? And what you would find is that basically the mass dimension of your diagram is just the mass dimension of this coupling. And since the loop diagram and the tree diagram are contributing to the same scattering amplitude, that means that the loop diagram also has to have mass dimension of the same mass dimension as the coupling GE. Okay. All right. But we know from experience that the loop diagram, the mass dimension of these loop diagrams, we can analyze just by counting factors of momentum in the numerator and propagator. Okay. So the loop momentum, the loop diagram, the mass dimension looks like that. Okay. So I have the loop part that we talked about before, and then I'm adding on parts of the vertices because these couplings have mass dimension. Okay. All right, so then I can do a little bit of algebra. Right? I know that those first two terms are just equivalent to big D, the superficial degree of divergence. Right, so then I can, and then taking D over to the other side, or GE to the other side, I find that the degree of divergence for this particular vertex goes like the mass dimension of this coupling minus the sum over all the rest of the vertices with the vertex, or what was V? I forgot. V was number of vertices. Yeah, number of vertices times the mass. So that's just a number, and the mass, and that's being multiplied by the mass dimension of these individual couplings. Okay. All right, and so what we see is from this general formula is what's going to happen. So we've said that our degree of divergence, if it's greater than or equal to 0, that diagram or whatever we're looking at is divergent. Okay, so now we have it written in terms of parameters of the theory, right? Instead of momentum or factors of momentum from a particular diagram, right? And we see that if all these guys have positive mass dimension, there's a good chance that we're going to be okay, right? Because they're going to cancel off the mass dimension of this guy, and we'll end up with something that's less than 0 for big D, right? But if one of those guys, just one of those guys, has a negative mass dimension, in other words, the mass dimension of this guy is less than 0, that's going to give us two minus signs, and I'm going to get something that adds to this, okay? And so you're going to get something that's non-zero, right? Positive, possibly, okay? Okay, and so, and anytime you have that case, you're going to get these uncontrollable divergences. So you're going to get these cases where you have to keep adding more and more and more counter terms, right, to cancel off these divergences, okay? And it's just because this factor of D increases with every added vertex of the nth type. So, if GN is has negative mass dimension, it's going to be every time we add that vertex in, to a particular process, or if we're just trying to normalize the theory, we're going to have to introduce more and more terms. Okay. So the general rule that you take out of this is that any theory that includes interactions with negative mass dimension couplings, it has to be non-normalizable. Okay. And we'll see examples of that. So we always write down Lagrange. So when we write down a Lagrangian, we know that it has. So in D, let's say 4 dimensions to make it easy. Okay. So in 4D, right, we would write down the Lagrangian. We would have the normal kinetic term for our scalar field, we would have a normal mass term. And then we could have choices for our vertices, right? So from this guy, we can tell that the mass dimension of the scalar field has to be 1, right? So what if I said, okay, I got this crazy theory, and I'm going to write down a phi to the 6th term, right, with some coupling, G, right? But I know that the mass dimension of the Lagrangian is 4, right? So I look at this and I say, oh, this guy has to have negative mass dimension to cancel off 2 of these, right? So that this term is mass dimension 4. Right? So this would be an example of, if you spotted this in a theory, you'd say, non-normalizable, right? I'm going to get uncontrollable divergences, which sounds like a horrible thing, right? But you can work out, according to the number of dimensions that you have, you can work out, if a theory, what the mass dimension of your couplings are. Right? You can solve it, and you get an equation that looks like equation 6. And so you find that these couplings are going to have negative mass dimension if what's n? N is the number of lines, the number of external lines is greater than 2d over d minus 2. All right, so what does that mean? So it means in the 2 cases that we're interested in, namely d equals 4, all gn with n greater than 4 have negative mass dimension. That's that case that I just showed there, right? In the case of 6 dimensions, any guys that have greater than 3 have negative mass dimensions. Okay, so that's why when we write down this phi cube theory, we haven't been writing down phi to the 4th terms, right? Because those are non-normalizable in this 6-dimensional case. Okay. Yeah. And it turns out that we derived this all for scalar fields, but it turns out any theory that you write down, that it contains vector fields, fermionic fields, tensor fields, if you want. Anytime you have, you look at the theory, you look at the Lagrangian, and you see couplings that are going to have negative mass dimension, it tells you right off the bat that the theory is non-normalizable. Okay. All right. So it tells you. So it's not telling you that the theory is garbage. It's just telling you that you got to cut it off somewhere, right? You're not going to be able to work, or integrate over all momenta, basically. Okay. All right, let's take a 2-minute break. And let me get my throat's getting dry. Let me just get a drink of water.
چیزا تو مسیج هم دیدی؟ جامعه چیز خواهر کردی؟ نه خوبی پژوهشی آها داشته حرف می‌زدی؟ استاد خانه هست یا همین کردی؟ حتی بخواه بزنم بخونم نه دیگه آماده که من برسیم همچین حرکتی رو نزد
trying to remember where we're going.
I have a question.
Yeah, go ahead.
It's non-renormalizable theories that you said are not garbage. We don't have any control on the imaginary particles in between, and they can have any momentum.
So that's the thing. With these non-normalizable theories, you can't work with loops.
Yeah.
You have to work, everything has to be true level. Right? Because as soon as you introduce loops, then that's when you run into problems. Right? So that's what I was saying, that they're effective theories.
They exist even if we don't consider them the theory, but in reality.
Yeah, we just work at, we're just at energies where they make a sizable contribution to any observable. The way it's argued. So we're at low enough energies that virtual particles aren't going to affect. We can still describe physics at some lower scale.
Yes.
Yeah. All right. Okay. So more discussion on this stuff. Okay. So we've seen, what did we just show? I can't even remember what was on the last slide. All right. So we've seen that any theory that has not couplings or parameters that have negative mass dimension are non-renormalizable. Okay. But what about theories where where superficially it looks like the Lagrangian's good to go, that all the mass dimensions of the couplings are positive? What about those cases? Well, we've already seen a prime example in our phi-cube theory that even those theories have divergences, right? The difference is that we can always write down counter terms, right, that obey any symmetries of the theory, whether it be continuous or discrete symmetries, that can have counter terms that we can dial to basically cancel off any of the divergences that we hit along the way when we're computing loops. Right? And it doesn't, we've been talking about vertices, so we've been talking about number of legs greater than 3, but the same argument applies to the 2-point function, which you can actually think of as a vertex. It's a 2-point vertex, right? And you look at the counter term. So we found that in that case the self-energy had some divergences, right? So we had to include some new vertex, right? And you say, well, what are the mass dimensions of these couplings? Well, the couplings are A, because this is a kinematic factor, k squared. So A, and then this thing's just a constant. Okay, so you can look at the mass dimension of these guys. It turns out that this guy's 0 and this guy's 2. Okay. So again, we have divergences, but we can write down counter terms that have mass dimension couplings that are greater than or equal to 2, or greater than or equal to 0. Right? And we can do this at every order in perturbation series and cancel off any divergences that we run into. All right. So we going back to what we call D, which is the superficial degree of divergence. Okay, so it's not superficial in the sense that it just wants to get a bunch of stuff and wear nice clothes, and you guys know what superficial means?
Yes.
Okay. All right. So it's not superficial in that sense. It's superficial in the sense that it's not exact. It's not an exact science. Okay, so we might have a diagram that diverges even if D is less than 0, right? Or it might be finite if D is greater than 0, right? So those are the two cases. So before we said if D is greater than or equal to 0, it's divergent, and if D is less than 0, it's going to be finite, right? But here we're saying we can run into cases where the opposite can be true. So what's the deal with those? Okay. It turns out that the latter case, where we have a superficial degree of divergence greater than 0, happens a lot in QED. And the reason is because when you write down the Feynman rules for QED, especially for fermions, the propagators not only have, the normal k squared minus m squared, but they come with some factors of k in the numerator. I'll just write function of k. I don't want to get specific, right? But these functions of k will contribute to the superficial degree of divergence, right? So if you looked at a diagram in QED, you might say, oh, it looks like I'm going to have, I've got a superficial degree of divergence. It's greater than 0, so this diagram is going to be infinite, right? It's going to have a divergence. But then you go and compute it, and you find out it's finite, right? And the reason is that superficially, it looks like there's momentum factors here that are going to blow up. But when you compute the whole numerator, there's terms canceling each other off, okay? So you end up with something that is finite in the end, okay? And we'll see examples of that next semester, all right? The other case where we have d less than 0, which seems to be good usually, and finite, we can have diagrams that diverge even in this case, okay, when d is less than 0, right? And in one case, so let's consider the case where we have 4 external legs, right? And so there we found that at tree level, it starts with a loop, right? Even though at leading order it's a loop, right? We don't have a fundamental 4-point vertex in our 5-cube theory. So we computed those diagrams, those box diagrams, right? So let's say I wanted to compute that thing to next to leading order, okay? So that means I'm going to have 2 loop diagrams, right? So I'm going to have the one diagram that has this loop and then this loop. So I would have to do 2 integrations here, okay? 2 loop integrations. So the first diagram we know is finite, right? The second diagram, if we counted up the degree of divergence, we would think that we'd be safe, right? But we end up finding that it's divergent, right? But what saves us is that we remember that every time we see this, right? This is like an insertion of a self-energy diagram, right? And every time we see an insertion of a self-energy diagram, we know that we have to include an insertion of the counter term diagram. Okay, so anytime you see this, even if it's inside of another diagram, you know that you have to include that counter term. Okay, and that's what saves you. That's what cancels off this degree of divergence, right? So you don't have lingering divergences laying around at the end of the day. Okay. All right, so those are the 2 kind of weird cases. Right, so this is the second diagram. It's what we would call a divergent subdiagram. Like I said, when you consider them in isolation, they have d greater than 0, right? So it looks like the theories might be non-normalizable, but every time you see that, you have to include the counter term. So we can say with certainty that all theories with couplings whose mass dimensions are positive or 0 will be renormalizable. So that's just restating what we said earlier about theories that have negative mass dimensions. So if you have a theory and you look at, you count up the mass dimensions of all your couplings, all your parameters, and they're all, equal to 0 or greater, you can say, okay, I can work with this theory up to all scales, basically, because I can renormalize it. All right. What are we doing here? Okay, so this will lead. So you know what? I think I'm going to stop right here because this is leading into second part of this talk or these slides, which has to do with the quantum. It's called the quantum action. Okay, so it's a different way of structuring perturbation theory. And I'll just say I'm running out of gas, so I'm going to save that for next week. Okay, I don't want to burden you guys with that as you're working on the midterm. Right? I don't want you to be thinking about the quantum action. Okay. So we'll talk about that next time. And after that, we'll start to talk about some different normalization schemes. Okay, so like I kind of alluded to last week, or last time, you know, there's different schemes, so different choices you can make as far as your counterterms. All right? Okay. All right, well, have a good weekend. And let me know if you have any questions about the midterm. Let me know.
I have one.
Okay.
My answer seems to be like one line.
That's what I want.